In the real case, we have that the logarithm of a product of two numbers is equal to the logarithm of the first number plus the logarithm of the second number. We also have this famous formula for a fraction, logarithm of a fraction of two numbers. What about the complex case? A similar formula in the complex case is not available. Let's just give an example to show this. If set 1 is equal to set 2, both of them equal to minus 1, then we have that the product of these two numbers are of course equal to 1. The logarithm of the product of these two functions are therefore equal to the, well, we are talking about the principal logarithm here in the first example, is equal to the logarithm of 1, which is using the general formula, is equal to ln of 1 plus I multiplied with the principal argument of 1. And the principal argument of 1 is of course 0, and the same for the logarithm of 1. So the logarithm of this, at least the principal logarithm of this product, is equal to 0. Let's now consider the logarithm of the first number, set 1, and of course the logarithm of set 2 is equal to this. The logarithm of principal logarithm of minus 1 is equal to, in the same as above, logarithm of 1, which is 0, plus I multiplied with the principal argument of minus 1, which is pi. And the same for the second number, which is the same number. So what we are seeing here is that when we are adding these two logarithms, we get 2 pi. I multiplied with 2 pi, which is not equal to 0, which was the logarithm of the product. So here we see that using the principal logarithm, we cannot use the same formula as we did in the real case, namely this formula. Of course, we can construct similar formulas involving the logarithm of a fraction of two numbers, and give example that we don't have this identity in the complex case either. What about the more general logarithm with not capital L but small l? What about that? Let's take an example of this. If we have set 1 equal to set 2 equal to I, then we have that the logarithm of set 1 is equal to the logarithm of I, which is equal to, using the general formula, the logarithm of the absolute value of I, which is 1. The logarithm of 1 is 0, and the argument of I is pi over 2 plus 2 pi k. Because we don't have a unique value in this case, we have a multiple valued argument. So when we are considering the sum of the logarithm of set 1 and logarithm of set 2, we obtain the following: I multiplied with pi plus 4 pi k. It's just twice such numbers. And let's just see what is this. Using some values of k, for example k equal to 0, then we get this number, k equal to minus 1, we get this number, k equal to minus 2, we get this number, k equal to 1, we get this number, k equal to 2, we get this number. Okay, now consider the logarithm of the product of set 1 and set 2, which is the logarithm of minus 1. Because I multiplied with I is minus 1. So what's that? Logarithm of minus 1 is equal to, the real part of it is the usual logarithm of absolute value of minus 1 plus I multiplied with the argument of minus 1. This is of course in the same way as before equal to 0. The argument of minus 1 is pi, which is the principal value, plus 2 pi k, where k is an integer. So let's consider similarly as above, what type of values could this be? K equal to 0, then we obtain this value, k equal to minus 1, this value, k equal to minus 2, this value, k equal to 1, we get this value, k equal to 2, this value, k equal to 3, this value. Now, let's compare this set of values with this set of values. It's not the same. We see that this set of values is richer than this value. It includes all the values in this set, but they are not equal. So what this means is that the logarithm, a general logarithm of a product, is not in general equal to the sum of these two logarithms.